Hi 11s. In this video, I'm going to be walking through a couple of questions that we've put together for OCR Chemistry Separate Science. So we'll start with the multiple choice section. Question number 1. Which statement describes the advantages of instrumental methods of analysis? So by instrumental methods, we are referring to analytical techniques which rely on machines. Now, there are two techniques that we've covered in our spec, which can be considered instrumental methods. The first one is IR, infrared spectrometry, and the second one is mass spectrometry. Now, in general, there are three main advantages of instrumental methods over lab-based tests. So by simple lab tests, we're talking about flame tests. We are talking about the typical anion tests, so the precipitate tests for halides, for example. Both of these are considered simple lab tests, simple laboratory tests. Instrumental methods have a couple of advantages. First, improved speed. They are much, much quicker. The second thing is improved accuracy. And thirdly, they're far more sensitive, so improved sensitivity. By sensitivity, what I mean is they can detect very small amounts of a substance given a very small amount of sample. So if we look at our options, option number 1A, instruments can analyze very small amounts, true, and can carry out the analysis slowly. Instrumental methods are quick, they have high speed. Instruments are very accurate, true, and use large amounts of substances. They don't have to, they can, like I said, they're quite sensitive. C, instruments are very accurate and carry out the analysis slowly. Again, the same disadvantage there, slowly is not true. And instruments are very accurate and can run all the time, and that is the correct answer. Question 2. A student tests a solution for chloride ions. She adds dilute nitric acid to the solution, followed by a few drops of silver nitrate solution. Why does she need to add dilute nitric acid to this test? So the test for the halide ions is the silver nitrate test, AgNO3. But prior to adding silver nitrate, she's adding dilute nitric acid. So let's have a look at the options and we'll try and eliminate any obvious incorrect answers. To increase the pH of the solution, well, we know this is an incorrect option because adding acid will decrease the pH. The closer you get to 1,0, the more acidic it is. So this is not true because adding acid would lower the pH. So it can't be A. Number 2, nitrate ions are needed for the test to work. So we've already discussed this briefly. In order to conduct a chloride ion test, you don't need nitric acid. The ion you need is Ag, because the ionic equation for this reaction is Ag plus Cl minus to form AgCl, which is a solid precipitate. And this solid precipitate is white in color. So this is the test that we're trying to conduct. So nitrate ions are not needed for the test to work. If we jump to D, this test only works in alkaline condition. If that was true, adding nitric acid is not going to help this. So a nitric acid will make the conditions more acidic. So this is not true because an acid was added. Now, if we go back to C, already by process of elimination, we know that C is correct, but let's talk about why. To make sure that no carbonate ions are present. Now, carbonate ions, CO3 2- ions, if they are present in the solution and we add silver nitrate, i.e. Ag plus ions, the two would actually react. Carbonate can also react with silver to form a precipitate. The name of the precipitate, or the identity of the precipitate, is Ag2CO3. And since this is a precipitate, we've got the solid state symbols. Now, silver carbonate is also a white precipitate. Silver chloride, which is the solid that we're looking for, or the test or the observation that we're expecting, is also a white precipitate. So if there were any carbonate ions in the solution, they would react with the silver ions and form a white precipitate, and this we would consider a false positive result, because we are seeing a white precipitate, but it's not due to the chloride ion. So by adding nitric acid, how does this help the situation? Well, if nitric acid is added, this is now the test for the carbonate ions. Acid plus a carbonate will react together to form carbon dioxide. This eliminates any carbonate ions and avoids a false positive result. So C is the correct answer. So to make sure no carbonate ions are present to avoid false positive results. Question 3. Which statement about a mass spectrum of a molecule is correct? So we'll look at mass spectrum again in a little bit more detail in the next question. Question 4 is also to do with mass spec. We're just looking at the graph in this particular question. So on the y-axis, we've got abundance. On the x-axis, we've got something called MZ, or mass to charge ratio. And just to give you a quick recap, a mass spectrum will look like this. So you have sort of vertical lines of varying heights, and the height represents the abundance, and the x-axis, like we just said, represents the mass to charge ratio. So option A, each peak represents an atom in the molecule. This is false. Each peak actually represents something called a fragment, and we'll talk about what a fragment is in the next question. B, the charge to mass ratio of the molecular ion peak is equal to the relative formula mass of the molecule. It's not the charge to mass ratio of the molecular ion peak, it's the mass to charge ratio. If you look at the x-axis, it's mass to charge, not charge to mass. But the mass to charge ratio of the molecular ion peak is equal to the RFM of the molecule. That is true, but the incorrect part was the first term. The peak with the highest relative abundance represents the molecular ion. Also incorrect. Abundance is the y-axis. The height of the peak does not represent the molecular ion. It represents how much of it you have. The molecular ion is the far right of the spectrum, is the peak on the far right. So it's this peak here. This peak here has the mass to charge ratio, which is equal to the RFM, and it's known as the molecular ion peak. So D is the correct answer of the molecule here. So looking at mass spec in a little bit more detail. So this question here, look at the mass spectrum of a carbon compound, abundance on the Y, mass to charge ratio on the X. We have random peaks here. And already we know, based on the last question, this peak here is equal to the molecular ion peak, which gives us the RFM, the relative formula mass of the compound we are testing. So in mass spectrometry, a compound is passed through the mass spectrometer. It's vaporized first, so it's in gas form, and it's passed through the machine. And we bombard lots of electrons in it. And through this process, we form a positive ion, and this ion is the molecular ion peak. Now, this ion is quite unstable. It will break into smaller fragments. A fragment is different components of different sizes. And these peaks here, each of these peaks is one of the fragments the molecular ion peak split into. So they represent different portions or different parts of the main molecule. The biggest mass to charge ratio you can have is the entire molecule intact, so the molecular ion peak. All of the other fragments are different parts of that molecule which have been split up. So the heaviest ion is the molecular ion peak, and it has the relative formula mass of the entire compound. So at GCSE level, the only real bit of analysis you need to be able to do is to look at the peak on the far right, know that it's equal to the molecular ion, and also know that the X value that you obtain from that peak is the relative formula mass. So the relative formula mass for this compound is 50 51, 2, 3, 4, 5, 6, 7, 8. So this, from this graph, we have figured out that the formula mass, relative formula mass of the compound that we're testing is 58. So looking at our options, which carbon compound is the mass spectrum from? So already we can eliminate options B and option C because these are not compounds, they're fragments. And we know that based on the charge. If we work out the relative formula mass of the first one, that's going to be 12 times 2 plus 1 times 2, which is equal to 26. So it can't be this one, so because that does not meet or match up with our 58, which is the total mass. If we double check D, 12 times 4, 48, plus 10 times 1, which is 10, gives us 58, which tells us that our compound must therefore be D, which is butane. Question number 5, which statement about atom economy is correct? Now, atom economy is a way of analyzing how efficient a process is. So the efficiency of reactions. It's a measure of the amount of the starting material that ends up as useful materials. So we can review the equation for it. So atom economy can be calculated by taking the total MR of your desired product, so the product that you're interested in, divided by the total MR of all of the products that are produced in that process. And atom economy is a percentage, so we need to multiply this value by 100. The higher the atom economy, so atom economy AE, the higher the atom economy, the more sustainable that process is, and the fewer waste products you are making. So you are aiming for a high atom economy. A business, for economic reasons, will want to have or will opt for a process which has a high atom economy because that leads to less waste. More of their products are the desired products, which is favorable. Looking at our options, a reaction that has only one product has a higher atom economy than a reaction that has two products, one of them being a waste product. That is true. If we take a generic example, A plus B, making just one product, C. C is our desired product, and C is the only product. So if we look at the atom economy for this reaction, total MR of C divided by total MR of C multiplied by 100 will give us 100. So it's 100% atom economy when we have reactants being added together to form one product. That will be much larger. That is the maximum atom economy you can have. So of course, A is true. B, a reaction with a low atom economy is more sustainable than a reaction with a high. We've already looked at higher atom economy is more sustainable. A reaction with low atom economy will produce less waste product. That's not true. If it has a low atom economy, it means it's making more waste products. To calculate the atom economy, you need to know the expected yield and the actual yield of products. This is not true, as we've just looked at the equation for atom economy. Yield is related to percentage yield, so this is a different calculation. So our final answer is A. Question number 6. Which statement describes what happens when a reaction reaches equilibrium? In an equilibrium reaction, we've got reactants producing products, and then we've got two directions. We've got a forward direction and a backwards direction. The forward reaction is where A and B react together to produce C and D. The backwards reaction is where C and D react to produce A and B. Now, during this process, or if we look at the rate versus time for this reaction, we can monitor the rate of the forward and compare it to the rate of the backwards reaction. So at the beginning of the reaction, the rate of the forward reaction is at its highest, and that's because you've got the largest, or the concentration of your reactants are at the highest. Now, this links to C5. If you've got more reactants, you've got more collisions, or the frequency of collisions is much higher, your rate of reaction is going to be high. As the reaction proceeds, your rate will decrease as you start to use up your reactant. Sorry. If we look at the backwards reaction, at the beginning of the reaction, our rate of the backwards reaction will be at its lowest because the concentration of product is 0 to begin with. As the forward reaction takes place, we start making products and C and D, or we start making C and D will then be able to react together to form A and D. So if we monitor the rate of the backwards reaction, that will increase until it reaches this point here. This point here, where the two lines merge, this is known as the equilibrium point. So at equilibrium, both rates are equal. So it's when the forward reaction and the backwards reaction happen at the same rate. So this is forwards, that is backwards. So looking at our options, the option that matches what we've just said is B. So the forward and backward reactions happen at the same rate at equilibrium. A is incorrect because it says forward reaction happens faster than the backwards. That's not at equilibrium. That happens when it's at the start of a reaction. C, the forward and backwards reactions stop happening. No, at equilibrium, both reactions are taking place, but they're taking place at the same rate. And the backward reaction happens at a faster rate than the forward. Also incorrect when we're talking about the equilibrium point. At equilibrium, both rates are equal. Question 7. A catalyst can be used to increase the rate of reaction. Which graph shows the mass of the catalyst as the reaction takes place? So a catalyst is something that is not used up in the reaction, and therefore the mass will be unchanged throughout the reaction. So if we have a look at the options, option A, the mass is changing, it's increasing over time. B, the mass of the catalyst is decreasing over time, as is D, the mass of catalyst is decreasing. C is the only option where the mass remains unchanged. It's a constant mass. So C is your correct answer. Question 8. Which of the following is the expression used to calculate concentration in grams per decimeter cubed? Concentration is the amount of substance you have per unit volume. In this case, we're looking at concentration, and you can have concentrations in various different units. You can have moles per decimeter cubed, moles per centimeter cubed. In this question, we're looking at grams per decimeter cubed, i.e. the mass per decimeter cubed. 1 decimeter cubed is equal to 1 liter. So if we look at the expressions given to us, A, the mass of solute in grams divided by the mass of solution in decimeter cubed. This is a correct definition because the mass of solute, i.e. the substance being dissolved to form the solution, divided by the volume of solution in the correct units, it's in decimeters cubed. So A is our correct answer. Let's look at why the others are incorrect. B looks very similar, but it says mass of solvent, which is not true. We're looking at the amount of substance dissolved in a unit volume. C, concentration is equal to mass of solute multiplied by volume. By looking at the units, we can actually see, we can figure out what the formula is. Grams divided by decimeter cubed. That slash here represents a division sign. So it should be grams over volume. So it can't be C because it's being multiplied. It can't be D because, again, mass is being multiplied by volume. And therefore the answer is A. Question 9, which statement is true for a reversible reaction when it's at dynamic equilibrium? So we've already looked at what equilibrium is, so we should be able to answer this question. The word dynamic just means the reactants are changing into products, products are changing into reactants. So we're saying that both processes are happening, both molecules on the left and the right are constantly changing into each other. So based on this, we can confirm that the answer is C. The rate of forward reaction is equal to the rate of the backwards. B is wrong because it says greater. A, the concentration of the products is increasing. That is not true. At equilibrium, concentration is constant. It doesn't necessarily mean the concentration of products and reactants are same. It just means they are constant. The value is not changing. D, the rate of the forward is greater than the rate of the backwards. Also incorrect because as we've established at equilibrium, rate of forward is equal to rate of backwards. Question number 10, look at the equation for a reversible reaction. We're given delta H, which is the enthalpy change or the energy change for the reaction, which is negative. The reversible reaction forms a dynamic equilibrium in a sealed container, i.e. no reactants are coming in, no reactants are going out. It's a closed system. Which of the following would move the position of the equilibrium to the right? Now, what we need to understand is when a change is made to the conditions of a reaction or a system at equilibrium, the system will change to oppose whatever change you've made. So this is the principle. This is Le Chatelier's principle. So we can use this principle to predict what would happen to the position of the equilibrium when we change factors like temperature and when we change factors like pressure. So let's review the effect of changing pressure and temperature on equilibrium. Let's look at pressure first. So we can do two things. We can either increase the pressure or we can decrease the pressure. If we increase the pressure, the equilibrium will shift to the side with fewer moles of gas. If we decrease the pressure, the equilibrium will shift to the side, whichever side has greater or a larger number of moles, it will shift to that side, moles of gas. Let's review temperature and then we'll apply it to this question. So temperature, again, we can do one of two things. We can either increase the temperature or we can decrease the temperature. Now, if we increase the temperature, the system will change to oppose this, this change in factor. So the equilibrium will shift to the endothermic direction, or in the endothermic direction. So increasing the temperature shifts it in the endothermic direction. It wants to use up that, it wants to take in that heat. If we decrease the temperature, it will have the opposite effect. The equilibrium will shift in the exothermic direction. So the question asks, which of the following would move the position of the equilibrium to the right? So first of all, we need to look at the delta H. That's an important piece of information we're given here. Delta H is negative, and if delta H is negative, that tells us that the forward reaction is exothermic. So we want to shift the position of the equilibrium to the right, i.e. we want to shift it in the exothermic direction. So if we have a look at our notes here, if we want to shift it in the exothermic direction, we need to decrease the temperature. Decreasing the temperature shifts it in the exothermic direction. So we can eliminate C because that says increasing temperature. We want to decrease the temperature. We also need to think about what we can do to pressure. We need to work out the number of moles of gas on either side. So on the left-hand side, we've got 5 plus 4, so 9 moles of gas on the left-hand side. And on the right-hand side, we've got 4 plus 6, which is 10 moles of gas. And they're all gas, which is good. So we can add all of those up. If we want to shift the position to the right, i.e. we want to push it to the side with more moles or a larger number of moles of gas, we need to decrease the pressure. So decreasing the pressure shifts to the side which has a larger number of moles of gas. So to conclude, we need to decrease the pressure, decrease the temperature. So the option that matches this is A. using a catalyst will not shift the equilibrium position. It has no effect on the equilibrium position. It only increases the rate of reaction. Final question, a nice easy one to finish off with. The table shows the composition of the Earth's early atmosphere compared with the atmosphere today. So we've got early followed by today. 4 different gases. Which gas has changed by the largest percentage from the early atmosphere to the atmosphere today? So if we look at the difference, that's 74% difference. We've got 20.5% difference. We've got 0.4% difference. And we've got 94.96% difference. So that is the largest change, and that's for carbon dioxide. Therefore, D is our answer. And that brings us to the end of the multiple choice section. Let's move on to section 2. This question is about properties of materials. Police bullet-resistant vests could be made from steel or Kevlar. The table shows some information about steel and Kevlar. We've got a couple of different points there. Density, we've got relative strength, flexibility, and resistance to corrosion. Describe and explain 2 reasons why bullet-resistant vests should be made from Kevlar instead of steel. So we've got to not only describe but explain, which requires the word because in our answer. It's a 4-mark question, so I'm expecting 2 marks per point, where 1 mark is for the description and 1 mark is for the explanation. So if we look at Kevlar versus steel, there are a couple of points, or there are a couple of different things why one might opt for Kevlar. So we can see that the density is much lower. We can see that the strength is much higher. It's more flexible, and it has a higher resistance to corrosion. So on all 4 scales, Kevlar trumps steel. So we can pick any 2, and we can discuss why we can make bullet-resistant vests from this material. So I'm going to pick density. Kevlar has a lower density. So this is my description. My explanation as to why bullet-resistant vests should therefore be made from something that's lower, has a lower density. It will be easier for the policeman or the police person to wear, to carry. My second reason, I'm going to pick the strength. So the relative strength is much higher. It's 5 times higher. So Kevlar is therefore stronger. We should therefore use this material because it's less likely to be, because we want them to be bullet resistant. If a material is stronger, the bullet is less likely, it won't be able to penetrate through that material. You could also talk about the other 2 points. So you could say that Kevlar is more flexible, and therefore it's, again, easier to wear, more comfortable to wear. You can move easily, you can move quickly. You can also talk about the last point, resistance to corrosion. Because it's highly resistant, it's less likely to corrode, and therefore the vest will last longer. So any of those would be fine, as long as you describe and explain for 4 marks. Question part B, look at the structure of Kevlar. What type of molecule is it? Now, just by looking at this diagram that's been given to us, we can tell that it's a polymer because it's got the standard structure of a polymer, the shorthand notation. So we know it's a type of polymer, but that's not specific enough. We need to give a little bit more detail and describe what type of polymer it is. Now, there are 2 types of polymers. It can either be addition or it can be condensation. To identify whether it's addition or condensation, we need to know what kind of monomers are involved in it. In addition, we are looking at alkene-based monomers. And in condensation, we need 2 different functional groups. Either the carboxylic acid and alcohol, which will go on to producing an ester link, and therefore polyesters, or we're looking at carboxylic acids and amine groups, which go on to producing an amide link, and therefore polyamide. This polymer diagram here has a special link, which is this bit here. This is what stands out to me. The C double bond O NH. This link here is an amide link. C double bond O NH is the link for an amide, and therefore it tells us that it must be a condensation polymer. If you want to be more specific, you can even say it's a polyamide. That's the type of molecule shown. How this differs, if you're interested in seeing how it differs from a polyester, an ester linkage will be carbon, oxygen double bond, and then just a straight O. This is your ester link. This is your amide link. We can tell that this is not an ester link because we don't have that second oxygen, and therefore it's our amide link. So condensation polymer, if you want, you can even write polyamide. Nanoparticles are being used to make a material that is even better than Kevlar at resisting bullets. Nanoparticles are often made of silicon dioxide. A silicon dioxide nanoparticle has a diameter of 18 nanometers. The diameter of a silicon atom is 0.22 nanometers. Estimate how many times larger the silicon dioxide nanoparticle is compared to a silicon atom. Give your answer to one significant figure. Now, the key term in this question is this command word, estimate. Whenever you're asked to estimate, estimation is when you use approximate values in a calculation to give you an approximate answer rather than an exact answer. So in this question, if we're asked to estimate, you need to round your values prior to calculating. So 18 nanometers, we need to round this to 1 sig fig since that's the level of accuracy this question is asking us to estimate to. So 18 nanometers, if we're going to estimate, we can round this number to 1 sig fig, which will be 20 nanometers. 0.22, which is the other number involved in this question, we can round this to 1 sig fig, which will be 0.2 nanometers too. So we're rounding to 1 SF, one significant figure. And now we can carry out this calculation because we're just estimating, so we can use our approximate numbers. 20 divided by 0.2, which gives us 100. So this is approximately 100 times larger. Part II, silicon dioxide is used as a catalyst. Suggest why 1 gram of silicon dioxide is more effective as a catalyst when used as a nanoparticle rather than a powder. So we're comparing the same mass, but the nanoparticle version rather than a powder. So first point, 3 marks. A nanoparticle or nanoparticles have a greater surface area to volume ratio than powders. So nanoparticles, that will be our first point. So in other words, for the same volume, nanoparticles have a much, much greater surface area. The reason why this is relevant when we're talking about catalysts is because reactions take place on the surface of a catalyst. So that needs to be included in our answer as well. So due to this, if we've got more surface, if we've got a greater surface area, that's going to enable more frequent collisions to take place. We've got a greater surface area, reactions take place on the surface, and so we've got more frequent collisions and therefore a higher rate of reaction or faster rate of reaction. Question 13. In the Haber process, nitrogen gas reacts with hydrogen gas. Ammonia is made. This reaction is a reversible reaction. Write the balance symbol equation for this reaction. So we are given nitrogen is reacting with hydrogen. It's a reversible reaction, so our reversible arrow to form ammonia. Now, our reaction is not balanced because we've got 3 hydrogens on the right and only 2 on the left. So if we put a big number in front, a big 2 in front of ammonia, we'll need to put a big 3 in front of hydrogen in order to make sure that we've got 6 atoms. 2 times 3 is 6 H's, 3 times 2 is 6 H's, so our hydrogens are balanced. And double checking our nitrogens, 2 times N, that's 2 nitrogen atoms on the right, and N2, 2 nitrogen atoms on the left. So balanced symbol equation done. Part B, the conditions used to make ammonia in the Haber process are pressures of 200 atmospheres and a temperature of 450 degrees Celsius. The reaction is an exothermic reaction. So that means forwards is a negative delta H value, exothermic. A company making ammonia increases the temperature used to 550. So they've gone from 450 to 550 degrees Celsius. What happens to the rate of reaction when temperature is increased? Increasing temperature will always increase the rate of reaction. So rate of reaction will increase. We're increasing the kinetic energy of the particles. They are colliding more frequently, and a higher frequency of collision leads to a higher rate of reaction. Part II, the company thinks that the increase in temperature will increase the yield, i.e. how much product of ammonia. Is the company correct? Explain your answer. So if we think back to that multiple choice section, increasing the temperature will always shift the equilibrium position to the endothermic direction. Now, in the Haber process, the forward reaction is exothermic. So if we increase the temperature, the endothermic direction is backwards, and that is what will be favored. And if we go backwards, we are reducing the amount of product and increasing the amount of reactants. So this statement is incorrect. The company is not correct, as higher temperatures favor the endothermic backwards reaction. This shift to the left-hand side will reduce the yield of ammonia. Part C. The company wants to reduce the cost of making the ammonia. They decide to reduce the pressure used to 150 atmospheres. Write about 2 disadvantages of using a lower pressure to make ammonia. If we review the Haber process, this time with the state symbols, we can see that we've got nitrogen and gas reacting with hydrogen and gas to produce ammonia, which is a gas. If we look at the number of gas moles on the right-hand side and the left-hand side, we've got 4 moles of gas on the left, 2 moles of gas on the right. If we reduce the pressure, linking it back to Le Chatelier's principle, reducing pressure, the equilibrium will shift to the side with more moles of gas. In this particular case, more moles of gas is on the reactant side. So by reducing the pressure, it may reduce the cost, but it's also going to reduce the yield. So that's point number 1. So the disadvantage is, so point number 1, lower pressure will favor the backwards direction since there are fewer gas moles on the right-hand side. And this will lead to a decrease in yield. So yield of ammonia will decrease, which is a disadvantage since they're interested in making ammonia. Secondly, we can think about the effect of pressure on rate of reaction. So if we increase the pressure, rate of reaction will increase. And that's because we've got more moles or more molecules in a given volume, which increases the frequency of collision, leads to a higher rate of reaction. Reducing the pressure will have the inverse or the opposite effect. So reducing the pressure will reduce the rate of reaction, Because the frequency of collisions will also reduce. So our second disadvantage is a slower rate of reaction. Okay, question D. Ammonia is used to make fertilizers such as ammonium sulfate. A student makes some ammonium sulfate crystals in a lab. She uses a titration method as shown in the diagram. So she has the acid in the burette, ammonia solution, and the indicator in the conical flask. She then adds the dilute sulfuric acid from the burette until the indicator changes color. The student then crystallizes the solution. She's left with impure ammonium sulfate crystals. What should the student have done to obtain pure ammonium sulfate crystals? So, number one, they need to repeat the titration until they receive concordant results, obtain concordant results. They need to note how much acid was required to neutralize the ammonia, and then they would have to repeat the experiment without the indicator. So the impurity, the major source of impurity is because they have not removed the indicator. In industry, the same reaction is used to make ammonium sulfate. The method used is different. Give one reason why the lab method or the laboratory method to make ammonium sulfate is not used in industry. In industry, they are working on a much larger scale. So to answer this question, you could say any of the following. You could say that in industry, they are working on a much larger scale. You can say that a titration is a batch process, not a continuous process. You can also say that the volumes of solutions are too large for the titration method. Question 14. In an experiment, a mixture of ammonium chloride and calcium hydroxide is heated. Ammonia gas is made, and we are given the balance symbol equation. The student adds 5 grams of ammonium chloride to an excess of calcium hydroxide. Calculate the maximum volume of ammonia gas that could be made at room temperature and pressure. 1 mole of gas occupies 24 decimeters cubed at room temperature and pressure. So the equation we want to use is moles. So the equation we want to use is moles of gas is equal to volume of gas in decimeters cubed divided by 24. So we know this equation is going to feature in this question, but at the moment we don't have the moles, so we need to calculate that out first. So we are given the mass of ammonium chloride. The ammonium chloride is being added to an excess of calcium hydroxide. So we know that we don't need to worry about calcium hydroxide, that's in excess. So the limiting reagent, and therefore the amount of ammonia gas is going to be dependent on the number of moles of ammonium chloride. So step 1, work out the moles of ammonium chloride, NH4Cl. Now we are given mass of ammonium chloride, so the equation we need to use is mass over mR. Mass of ammonium chloride is 5. The molecular mass of ammonium chloride is 53.5. So 5 divided by 53.5 gives us 0.0935 moles. So this is the number of moles of ammonium chloride. We are interested in working out the moles of ammonia, and we can see that the molar ratio of ammonium chloride to ammonia is 2:2, which is 1:1. So the moles of ammonia chloride used is equal to the moles of ammonia gas made. So ammonium chloride is equal to the moles of ammonia. So this tells us that the moles of ammonia is also 0.0935. So now we have our moles of ammonia. We can use this equation that we looked at earlier on. So we want to work out the volume of ammonia is going to be equal to the moles multiplied by 24. So 0.0935 multiplied by 24, and that gives us 2.24 decimeters cubed. Next question, part B. In another experiment, a student reacts sodium hydroxide solution with dilute hydrochloric acid. The balance symbol equation is given to us. 35 centimeters cubed of 0.075 moles per decimeter cubed hydrochloric acid are added to 25 centimeters cubed, 0.1 mol per decimeter cubed sodium hydroxide solution. Use the information to determine which reactant is in excess. So to determine which reactant is in excess, we need to calculate the moles of both of our reactants. And in this question, we are given volume and concentration. So the equation we need to use is moles is equal to concentration times by volume in centimeters cubed divided by 1,000 to convert that into decimeters cubed. So we can do a little table to organize our data. So using this equation, the number of moles of HCl be 35, the volume multiplied by the concentration 0.075 divided by 1,000, and this will give us 2.6 times by 10 to the minus 3 moles, so moles of acid. Doing the same for sodium hydroxide. Volume multiplied by concentration divided by 1,000. This gives us 2.5 times 10 to the minus 3. And this tells us that the acid is therefore in excess. We've got more moles of acid, which will go on to producing more moles of our products. Part II, to find the exact amount of dilute hydrochloric acid that reacts with 25 centimeters cubed of sodium hydroxide solution, the student does a titration. Look at the student's results. The rough titration is not shown. Use the student's concordant results to calculate the mean volume of HCl required. So concordant results, these are results which are plus or minus 0.1 centimeters cubed within that range. So if we have a look at the data values given to us, 36.3, 35.8, the difference between these two values is larger than 0.1. So these two results are not concordant. If we have a look at titration 3 and titration 1 and 2, again, these values are more than 0.1 out. And then looking at the titration 4, 36.2, we can see that 36.2 and 36.3 within that range 0.1. So these two results are concordant. Titration 2 and 3 are out of this range. So these are the two values that we can use to work out the mean. You can only use the concordant results when you're calculating the mean. So mean is calculated by adding the two values, dividing by the number of data sets. So divided by 2, that gives us 36.25 centimeters cubed. So that is our mean volume. Other titration, 25 centimeters cubed of potassium hydroxide solution are titrated with 0.2 mole per decimeter cubed sulfuric acid. 24.8 centimeters cubed of sulfuric acid are needed to neutralize 25 centimeters cubed of potassium hydroxide. Calculate the concentration. So again, a table, KOH, H2SO4. The concentration of acid was given in the question, 0.2. The concentration of sulfuric acid is what we're trying to work out. So let's start by working out the number of moles, and we can work out the number of moles of acid since we have both concentration and volume. So using N equals CV, number of moles is equal to 0.2, the concentration, multiplied by the volume. Since the volume is in centimeters cubed, we need to divide it by 1,000. This gives us 4.96 times 10 to the minus 3, and this is the number of moles of acid. In order for us to work out the concentration of base, we need to first work out the number of moles of base. Now, we can use our molar ratio to work out the number of moles of base. We can see that the molar ratio is 2 to 1. So if we have 1 mole of acid, we require 2 moles of KOH. In this question, we have used 4.96 times 10 to the minus 3 moles of acid, which means the moles of KOH will be this value multiplied by 2. We're multiplying by 2 because the molar ratio is 1 to 2 of 9.92 times 10 to the minus 3. So we have the moles of KOH. To calculate concentration, we need to rearrange the formula we've been using and make concentration the subject. So N equals CV divided by 1,000. Therefore, concentration, we need to multiply number of moles by 1,000 first. V to the other side, we need to divide both sides by V. So using this expression, concentration of KOH is equal to 1,000 multiplied by the number of moles we've just worked out, 9.92 times by 10 to the minus 3, divided by the volume of KOH. Now the volume of KOH was 25. This gives us an answer 968. This is our final answer, or you can round to the correct sig figs, 0.4, and that will get you 4 marks. Question 15. Ethanol is manufactured by reacting ethene with steam. The reaction is reversible and occurs in a closed system. We're given the balance symbol equation. We are given what delta H is. Delta H is negative, so the first thing I would do is write exothermic. So forward reaction is exothermic. 5% of the ethene is converted into ethanol at each pass through the reactor. By removing the ethanol from the equilibrium mixture and recycling the ethene, it is possible to achieve an overall 95% conversion. Explain why the conditions used for the reaction are chosen. So the conditions chosen, we've got a temperature 300 degrees Celsius, we have pressure 60 to 70 atm, and we're using a phosphoric acid catalyst. It's a 6-mark question, or let's consider each condition separately. So temperature to begin with. So for each of these conditions, we should talk about the effect on rate and the effect on the equilibrium position. So temperature, if we talk about rate, increasing the temperature will increase rate of reaction. However, higher temperatures will be expensive to maintain, and it will be expensive to generate as well. Next, we need to talk about the effect of temperature on the equilibrium position. So we've already looked at delta H. So delta H tells us the energy associated with the reaction. So it's an exothermic reaction or the exothermic process for the forward direction. If we increase temperature, the equilibrium will shift to the endothermic side. So increasing the temperature is going to shift it backwards. It will favor the backwards reaction because if forward is exo, backwards is endo. And increasing temperature favors the endothermic direction. And the second disadvantage is increasing temperature shifts position of the equilibrium left, and this will reduce our yield. So the conditions used, 300 degrees Celsius, it's got to be high enough that the rate is pretty fast, but it's not too high that it's costly, and it's not too high that our yield is affected significantly. So that's temperature. The next condition we need to talk about is pressure. So increasing pressure will increase the rate of reaction. You've got more molecules in a smaller volume, which will increase your frequency of collisions, therefore your rate. However, the disadvantage of high pressures, just like temperature, high pressure is difficult to generate and difficult to maintain. In terms of the effect on equilibrium position, we can see we need to consider the number of moles of gas on either side. So on the left-hand side, we've got 2 moles of gas. On the right-hand side, we've got 1 mole of gas. Increasing the pressure will shift to the side with fewer moles, which is going to be the right. So in this case, increasing the pressure will increase the yield because it favors the forwards direction. Increasing pressure, as there are fewer gas moles on the right-hand side. This increases yield. Next, we can talk about the effect of a catalyst. Uric acid catalyst is used. The catalyst has no impact on the equilibrium position. It does not affect how much product we make. It does not affect the yield. The only purpose is to increase the rate of reaction. So a catalyst will increase rate of reaction. There's one last point that is mentioned in the questions. By removing the ethanol from the equilibrium mixture and recycling the ethene, it is possible to achieve an overall 95% conversion. So we can also comment on the impact of removing ethanol from the equilibrium as it's made. This point here is referring to the effect of concentration. So I'll write that here. So concentration. Ethanol from the equilibrium mixture, we are reducing the concentration of the products. So removing ethanol is decreasing the concentration of our products. The equilibrium will always shift to counter that change, to oppose the change. And the way it will shift is to move in the forwards direction to try and replenish the ethanol that is lost. So reducing the concentration of ethanol will shift the equilibrium to the right, forwards direction, to replace the ethanol. Forward reaction is favored. A full answer, we've talked about all of the conditions, so temperature, pressure, the effect of a catalyst, and the effect of concentration on the equilibrium position and rate. Question 16. Look at the displayed formula of the monomer butene. What feature of butene molecules allows them to act as monomers? So earlier on, we looked at condensation polymers. Here is an example of addition polymers. Addition polymers require a double carbon-carbon bond. So that is the feature that allows butene to undergo polymerization. So a carbon-to-carbon double bond. Butene is an alkene. What is the general formula for an alkene? So for an alkene, the general formula is CnH2n. Butene undergoes addition polymerization to form polybutene. Write the displayed formula for polybutene. So we need to first write the carbon-carbon bond in the middle, but this time we're going to remove that double bond. In polymerization, when 2 butene monomers join, that double bond breaks. So we're going to show that double bond breaking. The next step is to extend the 2 bonds on either side of the carbon. We're going to draw the brackets, ensuring that the bonds that we've just drawn extend through those brackets. We're going to write an N. This represents the fact that this polymer has N number of monomers. It's a very large number. N can be any number. And to finish off, we need to make sure all of our groups are attached to the correct carbon. So on each carbon, we have a hydrogen and a CH3 group. So on the first carbon and on the second carbon. DNA molecules are polymers made from 4 different monomers. What are the monomers in DNA called? The monomers in DNA are called nucleotides. Polyesters are polymers made from condensation polymerization. What is the minimum number of functional groups that a monomer must have to form a condensation polymer? In condensation polymers, you need 2 functional groups. Now, these 2 functional groups can be on either side of a monomer, or it can be 2 separate monomers, where one monomer has one functional group and the other monomer has another functional group. So in the next question, we can see how these functional groups come together to form a polymer. So in this case, we're looking at polyesters, which are made from a carboxylic acid and an alcohol group. In this example, we've got 2 different monomers. One monomer is a dicarboxylic acid molecule. So it's got a carboxylic acid group on either side of that molecule. And the other one is a dialcohol group. So it's got an alcohol functional group on either side of that molecule. The box that you see is a symbol. It represents the middle portion of that molecule, which is irrelevant to this question. It does not get involved in the reaction. To show the formation. So in the formation, the first thing to do is to draw the ester link. I would start by drawing the link. So the ester link is a carbon, double bond oxygen, and then on the other side of the carbon, we've got a single bond to an oxygen. And that is that ester link that happens. In condensation polymerization, a small molecule is lost. Typically, that molecule is water, and we can see where this water comes from if we look at the functional groups involved. So we've got H2O, OH, and that H, which forms the water. The remaining part of that molecule links together, so we can form that bond between the carbon and that oxygen there. The water would have been lost in that process. So this is what we're drawing here. So we need to continue drawing the rest of that molecule. So next to that oxygen, we have a box, and then an O. And we're going to keep that bond extended to show that there are other molecules. This is an ongoing process. There are other monomers on the other side. On this side of the molecule, we've got our box, the carbon, double bond O, and then we need to extend that bond out, and then we can write an N to show that, again, this is an ongoing process. This is just a small proportion or small part of that big long chain polymer. So a mark for the link, and then you get a mark for making sure that the ends are open, to make sure that you don't draw in the hydrogen on one side and the OH on the other side. Next question we've already answered. What is the formula of the molecule that is eliminated when the polyester is formed? It's a water molecule. Nylon is another polymer formed in condensation polymerization. Nylon can be made from hexane dichloride and hexane 1,6-diamine. Both chemicals are highly corrosive. A solvent is needed, which is highly flammable. Describe how to make nylon in a lab. So this is one of the experiments that you need to remember. So first, we need to make sure that you pour the hexane dichloride on top of the diamine solution. We want to minimize mixing. So step 1, pour the dichloride on top of the diamine solution and minimize mixing. Now, your teacher would have either demonstrated this in class or at least shown a video. If you haven't seen it, I highly encourage you, I recommend that you go and watch this video, because It is a common question that comes up. You need to be able to describe the method and also be able to recall the safety precautions for this practical. So if I draw the beaker here, you'll have one layer, which is the diamine solution, and then you'd have a second layer, which is the dichloride. This interface here is where your nylon is produced. So you can pick the thin film of nylon, which is produced at the interface, and you can use tweezers. And you want to do this slowly. And then lastly, you want to make sure that you wash the thread to remove any corrosive chemicals. Okay, next, as I mentioned, you need to also be able to describe the safety precautions. So describe and explain 3 precautions needed to control the hazards. Since the chemical is flammable, as mentioned, avoid any sources of ignition, such as naked flames. And we've got to not only describe but explain. So avoid naked flames because solvent is highly flammable. Wear disposable gloves because the reagents are corrosive. And also wear eye protection for the same reason. Reagents are corrosive. Question 17. Carbon dioxide is one of several greenhouse gases, which is made from the combustion of fossil fuels such as coal, gas, oil. Between 2010 and 2016, the total percentage increase of atmospheric carbon dioxide has been about 2.5%. During the same time, the increase in mean global temperature has been only 0.05 degrees Celsius. The table shows the amount of carbon dioxide produced in a large city in 2010 and 2016. Look at the row for electricity generation. Calculate the percentage increase of carbon dioxide produced. Okay, to work out percentage increase, we want to first work out the difference. So 900,000. Take away 750,000. Divide by the original 750,000. And since it's a percentage, we need to multiply by 100. And this will give us 20% increase. Part B. Some scientists think there is a link between the amount of fossil fuels burnt and climate change. The data in the table does not support this view. Suggest reasons why. So we're trying to find evidence which does not support the link between fossil fuels burnt and climate change. And we need to use the data to explain. We are given various sources of carbon dioxide. We are also given data which shows the percentage increase in carbon dioxide within these 6 years. The reference to temperature is in the text above. So during the same time, the mean global temperature is 0.05 degrees. It's worth noting that the data given is for a large city, so that could be a first point. So it's difficult to comment. We don't have enough data, as this data is for a particular city, whereas the temperature change is the mean global temperature. So our first point is that the data is limited, as it's for one city and not a global figure. So data is limited. So the table does not support this view as we don't have enough data. Secondly, we can say that there was a significant increase in carbon dioxide. However, the effect on mean global temperature was quite minimal. So that's one way you can argue that the data does not support this view. Point mentioned in the text. So between 2010 and 2016, the total percentage increase of atmospheric carbon dioxide has been about 2.5%. So despite the large increase in carbon dioxide emission, the percentage increase of carbon dioxide in the air is much less. So that could be our third point. Much less than the increase in CO2 emissions overall. Iron rusts when it gets wet. The word equation for rusting is iron plus water plus oxygen forms rust, which is hydrated iron 3 oxide. The question is, balance the symbol equation for the formation of rust. So we are given the symbol, we just need to complete. So I would start by balancing the iron first. So we've got 2 atoms of iron on the right and only 1 on the left. So we can start. So we can put a 2 there. Then we can have a look at the hydrogen. So we've got 3 lots of water and therefore 3 lots of H2. So that's 6 hydrogen on the right and only 2 on the left. So we can put a 3 there. So that 3 times 2 gives us 6. And then we've got to balance the oxygen last. So at the moment, we have 3 times 1, so 3, plus O2, which is 5 oxygens on the left. And on the right, we've got 3 in Fe2O3 plus 3 lots of H2O. So that's 6 oxygens. So what we can do is, so this is not balanced. It's also going to be difficult to balance since the numbers we're trying to find a common multiple between is 5 and 6. So the first thing we can do is to double our values here. So we can double 2 and 3 so that it's 4, 6. And as a result, we're going to have to double this side to 2. If we check the numbers of oxygens again, this time round, we've got 6, 7, 8 oxygens on the left. And on the right, we've got 2 lots of hydrated iron oxide. So let's consider the iron oxide first. So in the iron oxide, we've got 3 oxygens, and in the water, we've got 3. So in total, we have 6 oxygens in hydrated iron oxide, but we've got 2 lots of hydrated iron oxide. So in total, we've got 12 oxygens. We need an additional 6 more oxygens on the left-hand side in order to balance the number of oxygens. And if we want 6 more oxygens, we need to multiply the oxygen molecule by 3, because 3 lots of oxygen molecules will give us 6 atoms of oxygen. So if we do another final check, we've got 12 oxygens on the right, and on the left, we've got 6 in the water, plus 3 times 2, which is an additional 6. Therefore, we've got 12 oxygens on either side. Have any multiple of this balanced equation. So if you wanted, you could have 2 lots of iron, 3 lots of water, plus 1.5 lots of O2 to form 1 lot of hydrated iron oxide. So this is also an option. Okay, final question. 1 kilogram of iron bar is left outside in the rain. All of the iron turns to rust. The rust forms at a rate of 60 grams per day. Calculate how long it will take for the iron bar to turn completely to rust. Give your answer to the nearest day. And this is a 6-mark question. So let's rewrite the equation from the first part again. So Fe plus 6 lots of water plus 3 lots of O2 will form 2 lots of iron 2O3 H2O. So this is the reaction that's going to take place. And we've got 1 kilogram of iron. And we're trying to, and all of that is going to turn into the iron oxide, which is our rust. And we're trying to work out how long this process will take. So first of all, we need to work out the number of moles of iron that we have. We've got 1 kilogram, but we need to convert that to moles. So moles of iron is going to be mass divided by mR, which is 1000 divided by the atomic mass for iron, which is 55.8, is 17.92 moles. So this is what we're working with, the number of moles of iron that we're working with. We know that the molar ratio for this particular reaction is 4 to 2, i.e. 2 to 1. So if we've got 2 moles of iron, that will go on to producing 1 mole of rust. So if we have 17.92 moles, we will go on to producing will be 17.92 divided by 2, which gives us 8.96 moles. So this is the number of moles of rust that we're going to form during this process. Converting that to mass, because we're going to be working out the rate, or we're going to be using the rate, which is based on mass. So mass of rust is going to be the number of moles multiplied by the molecular mass. So 8.96, which is the moles of rust, multiplied by the mR of rust, will give us the mass of rust, which is 1,914 grams. So this is the total mass of rust that we're going to form. So number of days taken will be 1,914 divided by 60, which gives us 32 days. So we'll write that on our answer line. And that brings me to the end of this video.